Hello students, welcome back. Myself, Srimati Ranjana Bandare, Assistant Professor, Department of Mathematics, Government First Grade College, Hulkoti. So, in this video, I am going to have discussion about BSc Third Sem Paper 1 Algebra and Number Theory, Third Unit Group Theory. And particularly we have the discussion of permutations and symmetric groups. First we shall define what is permutation. If S is any non-empty set, then a 1 and onto mapping from S to S is called as a permutation on S. Example, consider a set S is equal to containing the elements 1, 2 and 3. Let us define a function f from S to S by f of 1 is equal to 2, f of 2 is equal to 3 and f of 3 is equal to 1. So clearly we can say that the function f from S to S is 1, 1 and onto. So this function itself we are going to call it as a permutation. This permutation f is denoted by this way also, which is called two-line form. So here in the first row we are going to write the elements, and in the second row we are going to write the corresponding images. It is understood that image of 1 is 2 and image of 2 is 3 and image of 3 is 1. And the same can also be written in this way also, that is in only one line. This is one line notation. So here it is understood that the image of 1 is 2 and image of 2 is 3 and again the image of 3 is 1. So which both of which means the map f maps 1 to 2, 2 to 3 and 3 to 1. So other permutations on the set are these one. F1 is equal to, so 1 is mapped with 3, 2 is mapped with 1 and 3 is mapped with 2. So this we can write in the form of one line notation as 1, 3, 2, and this is another permutation F2. So in the first row 1, 2, 3 and in the second row 3, 2, 1. That means 1 is mapped with 3, 2 is mapped with 2 and 3 is mapped with 1. So this can also be written only by writing 1 and 3. It is understood that the image of 2 is 2 itself. And this is another permutation F3. So where 1 is mapped with 2 and 2 is mapped with 1 and 3 is mapped with 3. So we have another permutation where 1 is mapped with 1, 2 is mapped with 3 and 3 is mapped with 2. And the last permutation is 1 is mapped with 1, 2 is mapped with 2 and 3 is mapped with 3. That is nothing but the identity permutation. So next we shall write the theorem. The set C of S of all permutations on a given non-empty set forms a group under the composition of mapping. So we have to prove that the set of all permutations on the given set forms the group. The binary operation is the composition of mappings. So we know that to prove that it is a group, we have to prove the four laws: closure, associative, identity, and then the inverse law. The first one is closure law. Let F and G be two permutations on the set S. Then we know that both F and G are 1, 1 and onto mappings. And also we know that composition of map F into G is also 1, 1 and onto. Because we know that if F and G are both 1, 1 and onto, then their composition is also 1, 1 and onto. And hence we can say that F into G belongs to C of S. Hence, composition of mappings is a binary operation on C of S, and hence the closure law is satisfied. Associative law. Let alpha, beta and gamma belongs to C of S. Then, since composition of mappings is associative, we have alpha into beta into gamma is equal to alpha into beta into gamma. The next one is identity law. Consider the identity mapping I from S to S. It is defined by I of x is equal to x for all x belongs to S. Since it is an identity mapping, X is mapped with X itself. So, and we know that the identity mapping is clearly 1, 1 and onto. And I belongs to C of S. And consider any other permutation F belongs to C of S, then we know that F into I is equal to I into F is equal to F, because I is the identity mapping, and hence if you are operating with F, again we get the same element F only, and hence I is the identity element and which belongs to C of S, as it is 1 1 and onto, and hence we can say that the identity law will be satisfied. Fourth one, inverse law. If F from S to S is 1 1 and onto, then we know that F inverse from S to S also exists, and it is also 1 1 and onto by the properties of functions, and F inverse belongs to C of S, and we have F into F inverse is equal to F inverse into F is equal to identity mapping. That is, the identity mapping means it is nothing but the identity element in C of S, and hence we can say that the C of S satisfied, that is the set of all permutations on the set S, satisfies all the four properties, and hence we can say that it is a group with respect to composition of mapping as a binary operation, and this group itself we are going to call it as a symmetric group. So that is, symmetric group is, if A is a set containing n elements, then the group of all permutations of A is called as the symmetric group of A on n elements, and it is denoted by Sn. So the symmetric group is denoted by the symbol Sn. If a set A contains n elements, then the symmetric group contains n factorial elements. If a set A contains the n elements, then the symmetric group contains n factorial elements. So the next we are going to define the cycle. A permutation alpha on a finite set A is said to be a cycle of length k if there exist distinct elements A1, A2, A3, so on, AK belongs to A such that alpha of A1 is equal to A2, alpha of A2 is equal to A3, alpha of A3 is equal to A4, and then so on. Lastly, alpha of AK minus 1 is equal to AK, and alpha of AK is equal to A1. And for any other elements, AI belongs to A, I is not equal to 1, 2, 3, so on up to K, alpha of AI is equal to AI. That means except all these elements, the image of AI element is AI only. Okay, then we are going to call that alpha as a cycle of length K. We denote the permutation by, so this permutation itself we are going to denote like this way. It is understood that the image of A1 is A2, image of A2 is A3, similarly image of AK minus 1 is AK. So except all these elements, the image of remaining elements are the image, they only. That means the image of AK plus 1 is AK plus 1, AK plus 2 is AK plus 2, and AN image is AN only. Transposition. A cycle of length 2 is called a transposition. Theorem. Every cycle can be expressed as a product of transpositions in infinitely many ways. The proof follows like this. Consider the cycle of length n. Let we have a1, a2, a3, so on up to an minus 1, an is equal to. So it can be written it as a cycle of length 2. That means a1, a2, a1, a3, a1, a4, like this one, or this one, an, a1, an minus 1, a1, an, and let it be p of n. So we are going to prove the theorem by mathematical induction. And we know that while using the mathematical induction, we have the three steps. The first one is we are going to prove that the result is true for n is equal to 1. And assuming that the result is true for n is equal to k, we are going to prove that it is also true for n is equal to k plus 1. Instead of taking the result is true for n is equal to 1, so here we are going to prove the first step is the result is true for n is equal to 3. That is, we have considered P3 is equal to, it is a cycle containing the two elements A1, A2, and then another it is A1, A3. So A1, A2 means it is understood that the image of A1 is A2 and the image of A2 is A3 and the image of A3 is A3 itself. And here image of A1 is A3, image of A2 is A2 and image of A3 is A1. So find the product of these two. That means we can say that here A1 is mapped with A2 and A2 is mapped with A2. That means we get the image of A1 as A2. And here A2 is mapped with A1 and here A1 is mapped with A3. Therefore, we can say that the image of A2 will be it is A3. And here A3 is mapped with A3 and here we have A3 image is A1. So therefore, we can say that A3 is mapped with A1. So just see this one. So here, therefore, we can say that the product of these two cycles is it is A1, A2, A3. And hence we can say that the statement is true for n is equal to 3. Let us assume that the theorem is true for n is equal to k. That is, we have the cycle of length k, a1, a2, a3, so on up to ak minus 1 ak. So this we can write it as the product of 2. That means the transpositions, cycle of length 2, a1, a2, a1, a3, a1, a4, like this one. So consider the product of all these. That is the right hand side. So we have considered this one and along with this one we have multiplied the another element, another cycle of length 2, that is A1 AK plus 1. So here the theorem is true for all these one, that means up to from A1 to AK. So we can write as it is, and here this one, the product of this transposition we can write this way, that is A1 is mapped with AK1 and AK1 is mapped with A1. So remaining all the elements have the same images. So now find the product of these two so that we get this one. So here we have the image of A1 is A2, image of A2 is A3, and image of AK minus 1 is AK, image of AK is AK plus 1, AK plus 1 is mapped with A1. So by seeing this one, we get it is a cycle of length K plus 1. So therefore we have assumed that the result is true for n is equal to K, and we have got that it is also true for n is equal to K plus 1. And hence by mathematical induction we can say that every cycle can be expressed as a product of transpositions. So now consider it is in infinitely in many ways. So now consider AI AJ is one cycle and another cycle we have considered as AJ into EI. So it is nothing but the product of these two means we get it as a 1. So thus if we multiply the original product by any number of pairs of these types, which will not change the cycle but it will increase the number of transpositions in the cycle, and thus we can say that every cycle can be expressed as a product of transpositions in infinitely many ways. So next we are going to study even and odd permutations. A permutation in Sn, a permutation Sn is called even if it can be expressed as a product of even number of transpositions, and it is called as odd if it can be expressed as a product of odd number of transpositions. So here we have the note, a product of two even permutations is even and the product of two odd permutations is even. A product of one even and one odd permutation is odd. And we have the theorem, this one, in a symmetric group Sn where n is greater than 2, the number of odd permutations is equal to the number of even permutations. So we have to prove that the number of odd and even permutations are equal. So let us consider F1, the set containing the element F1, F2, so on up to Fp be the set of all odd permutations, and the another set G1, G2 up to GQ be the set of all even permutations. Now multiply this first the set of all odd permutations by f1, so that we have f1 square, and the second element becomes f1 into f2, the third element becomes f1 into f3, and last element becomes f1 into fp, which are distinct and they all are even permutations. Since we know that the product of two even permutations is even, but these are p in numbers and the total number of even permutations are q in number. So therefore we can say that p is less than or equal to q. So now multiply the set of all even permutations by f1. So then we'll get f1 into g1, f1 into g2, like this way, f1 into gq, which are all distinct and they are all odd permutations. Since we know that the product of an odd and even permutations is odd, but these are q in number. So we can say that q is less than or equal to p. So from 1 and 2, we have p is equal to q, p is equal to q, and p plus q is equal to n factorial, the total number of permutations on the objects. So thus we can say that the total number of even permutations is equal to total number of odd permutations. And we have p is equal to q, so that is n factorial divided by 2. And this is another theorem which we can prove. And for this one, we have the following references. So I hope you have enjoyed the video. Thank you.